So it's my pleasure to introduce Marc, who's going to talk about recent results that joined with his former PhD supervisor, Alessandro, about how to implement LQRs and optimism in an efficient manner. Marc's been on this problem since forever. I think his PhD was partly devoted to LQRs and LQGs and portfolio optimization, and like he just loves the linear stuff. And I'm very delighted that he was going so hard at this problem, and they came to this very interesting result, unexpected result, I would say. Yeah, like Marc has done quite a bit of other works like Thomson sampling, and we just heard that some new exciting paper is going to come out about generalized linear models with bandits. There was one version of the ICML, so lots of interesting works coming from Marc. So without further ado, Marc, do you want to take the stage?
Yep, thanks a lot, Csaba, for the introduction, and thanks also to Gaglay and Chiara for organizing this series of seminars. It's a real pleasure to be here and to have the opportunity to present our work. So, as you mentioned today, I'll talk about our ICML paper with Alessandro entitled Efficient Optimistic Exploration in Linear-Quadratic Regulators via Lagrangian Relaxation. So it's actually a quite long title, but hopefully by the end of the presentation, we will have a better understanding of those keywords and how they put together. So let's start. So in this work, we consider the standard reinforcement learning problem, where we have an agent that interacts with an environment to achieve some task. And in practice, at each time step, the agent submits a control or an action, UT, it's the UT here, to the environment, for which he receives a quost CT quantifying the quality of this control given the current state of the system. And then this environment dynamically evolves to a next state, and the process repeats for some time. So in the tabular setting, so when we have finite state and action spaces, this problem is relatively well understood. It's the MDP setting. But we focus here on the more challenging setting where the state action space is infinite. And to this end, linear quadratic regulators, or LQR for short, it offers a very powerful and neat framework because it allows to consider continuous state and control variables. It's infinite state space. But of course, this comes at the cost, and the cost here is to impose a specific parametric structure on the environment. So mainly the dynamics are assumed to follow linear modeling. So the next state is given according to a noisy linear mapping in the current state and control, while the cost is a quadratic function in the control state. So the motivation behind the studies of LQRs are twofold. First, from a control standpoint, so when we know the environments, it's one of the very few control problems with continuous state and action for which we can actually compute the optimal policy and solve the planning problem. We can also prove that this optimal policy exists, etc., etc. And as a result, it became kind of the standard since the seminal work of Kalman, and it's now widely used in the industry for like 40 years, with many applications ranging from like robotics to finance in particular. So then from a learning point of view, it allows us to focus on the key difficulties arising in reinforcement learning when we deal with infinite state and action spaces. And somehow one can see linear quadratic regulators as the reinforcement learning counterpart of what would be a linear model for bandits. So because of this theoretical and practical importance of linear quadratic regulator, the objective when designing a reinforcement learning strategy that we have to keep in mind is to offer both optimal or close to optimal performances, but while remaining as computationally efficient as we can, because those strategies are used in the real world. And to do so, we face two main challenges. So first, we have the well-known exploration exploitation dilemma to address, because we are controlling an unknown environment. And also, we have to care about state stability. And this new challenge is in sharp contrast with what we have in MDPs, mainly because now that we deal with an infinite state and action space, we need to prevent the learning process to drive the state to explosion. So I would say that these two challenges are equally important, but somehow orthogonal. And in the paper, we propose contribution for the two aspects of the problem, but in this presentation, I'll mainly focus on the exploitation challenges. Okay, so the outline of the talk is the following. First, I'll precise the setting, and I'll introduce the notations that we need to build on formal basis. Then I'll take quite some time to review the exploitation dilemma in LQR. And first, because I think it provides a lot of insights about the challenges at stake, and also to highlight the gap that is in the literature that drives this work, mainly the need to design efficient, confidence-based strategies. So then I'll present the solution we came up with that builds on optimism and Lagrangian relaxation. Okay, so let's start with the setting that we consider in this work. So it's the LQR, so it's a model-based control problem with very specific structure. The cost is assumed to be quadratic in the state X and the control U, which are continuous variable leavings in Rn and Rd respectively. And the cost is parameterized by two PSD matrices Q and R that are known to the agent. So we know about the cost. But on the other hand, the dynamics is assumed to follow a linear modeling. So the next state is a noisy linear mapping of the current state and control. And this linear mapping is parameterized by two matrices A star and B star that are this time unknown to the agent. And so since those are the important parameters here, I will often summarize them in a single parameter theta, and I will use the two representation indifferently when it's the most convenient. Okay, so in LQR, the control objective is to find a stationary policy that maps states to control and that minimizes the cost. And we evaluate the quality of the policy pi by the long-term average cost. And we denote this by J pi of theta. So it's the average cost induced by the policy pi for the parameterization theta over an infinitely long trajectory. And when the problem is optimally controlled, I will denote by J of theta the optimal performance for this parameterization. Okay, so that's the structure. So one of the very nice features of this linear quadratic structure is that despite that we have continuous state and control variables, we can still solve efficiently the planning problem. So because we can do this by solving a Riccati equation whose complexity scales basically with the cube of the dimension of the state. And formally for any parameterization theta, we can obtain, so by Riccati equation, the optimal policy pi star. And it turns out that this policy pi star is linear in the state encoded through a control matrix that I denote K of theta. So that's a very, very nice feature, and it's kind of its singularity among the control problem with continuous state and action. So obviously, what we would do if we knew the true parameter theta star is to take the best policy associated to it. But we have no idea a priori of what is this parameter. Yet the second nice feature of this linear structure is that we can efficiently learn this unknown parameter. So mainly at each time step, given realization of the trajectory we observed so far, we can use recursively squared to maintain online not only an estimate, theta hat, but the whole confidence set, so a set of plausible parameters that contain theta star with high probability. And this is what is represented on the figure below. This confidence set that we denote curly C, it's actually an ellipsoid and shrinks over time as we accumulate information. So here, now we see that in this setting, we can efficiently compute an optimal policy given a parameterization for the system, and we can leverage the realization of the trajectory to learn the true dynamic. So we are now ready to look at the reinforcement learning problem. And despite that the environment is unknown a priori to the agents, the objective is to input a sequence of control that minimizes the regrets so that the cost that we suffer over the trajectory are as close as possible to the optimal average cost that we would incur following the best policy pi. And as it's well known, the main challenges in designing such strategy is to properly balance between exploration and exploitation. Because we want to leverage what we learn, to exploit the acquired knowledge, to minimize costs, but to do so, we need to introduce just the right amount of exploration to learn the optimal policy and perform better in the future. Okay, so let me now take a bit of time to review the different strategies we can think of to address this trade-off and provide you with a brief overview of the literature. So to begin with, let's look at the most naive strategy we can think of, that is the greedy strategy, which consists at each time step to follow the optimal policy associated with the current least square estimate. So this is in LQR, it has the following structure because the controller is linear in the states. And of course, we can't really expect greedy to be a good strategy. We will see that it's not the case. But I'm presenting this first because it provides, because it has triggered a recent trend of research as it provides a lot of insight on the exploitation dilemma at stake. So by designing this strategy and its performance, it's tied to the consistency of the induced least square estimate because we're greedy with respect to it. And so it's interesting to look at what happens to the sequence of estimate over the trajectory, which is what I illustrate here. Say, if we run greedy on an infinitely long trajectory and plot the sequence of estimate, we obtain this red trajectory, and we see that it converges relatively fast to a limit point that I denote theta infinity 1. And this might seem very promising, but unfortunately, if we repeat exactly the same experiments, we'll get this. Another trajectory, the blue one, that converges to another limit point, theta infinity 2. And essentially, this means that the greedy strategy does not yield almost sure convergence for the sequence of estimates, but only a convergence in distribution. And this convergence takes place on some manifold that is denoted curly SC, which is what I call the self-coherent set. And this self-coherent set consists in all the parameters, theta, such that one optimally controlled leads to a predicted dynamic. So this corresponds to the left-hand side of the equation here, that coincides with the observed dynamic, which is the right-hand side of the boxed equation. And it means that, and that's at first the good news, that greedy achieves very fast what is called in control closed-loop identification, because prediction coincides with observation. Okay, so it's a good point, but unfortunately we can see on the drawing that it fails to achieve what is called open loop identification because we don't identify correctly the true parameters. And this lack of identifiability leads to suboptimal performance. This is what I illustrate here, where I drew for each parameters onto the self-coherent set, so each potential limit point for the greedy strategy, the difference in performance between the greedy controller and the optimal controller. And this is the suboptimality function delta J that I present here. So we see that this function is not flat, and as a result, each limit point associated, each limit point in the self-coherent set is associated with a suboptimal performance, and so the regret of the greedy strategy is simply linear. So what I display here is not novel at all. It's common in bandit and reinforcement learning in general. I could have drawn basically the same thing for linear bandits, but it also has been described for LQR in the early 80s. For instance, we have the work of Polderman, who fully characterized this self-coherent set and the shape of this suboptimality function, delta J. It means that there is an exploitation trade-off, but it has been recently at the core of the result of Shimkovitz and Foster and Castle et al. So it's at ICML this year, so very recently, who provided a lower bound and formalized that square root of T regret is unavoidable in the LQR setting. And this directly follows from the structure of the self-coherent set and the shape of the suboptimality function delta J. So it means that there is an exploitation issue, and it comes from this lack of identifiability. And so the most natural idea is to inject some additional noise into the system to help in discriminating within this self-coherent set where is the true parameter.
Mark,
so that's the, yes?
Quick clarification question about this.
Yes?
Lower bound. So this doesn't seem to be the end of the world.
The square root of T lower bound?
Yeah.
No, actually all of those results is expected, but what's funny is that this lower bound, like it's very, very recent. And although in the 80s it was very clear that there is an exploration issue and that the problem is like probably hard, we have to design carefully the exploration exploitation strategy. Recently, there were some feeling that maybe we can hope for fast rate in LQ because we have a strongly convex structure for the costs. And so basically we kind of, I think as a community, we kind of rediscovered and formalized findings that were already known in the 80s. And that explains this correlative T lower bound.
So just to clarify this again, this correlative T lower bound is for certainty equivalence?
No. Sorry, the certainty, the correlative T lower bound is for like minimax regrets in LQ in general. Okay. It's just that it really arises from I mean, at least it can be understood when looking at the behavior of the greedy strategy. It's I think what emphasizes this result.
All right. I'm not sure, but I'm less confused. So let me poke a little bit more. So sorry, this lower bound is for the high probability regret or the expected regret?
Expected regret.
Okay, that makes it interesting.
Yes. No, it's a really says that the problem is hard.
Yeah, but still it's a worst case result, right? So if you assume like further things, like some eigenvalues that are lower bounded for Q and R,
is it also
then you can do really better than this, right?
No, it's really in the standard regime. So it's under the standard hypothesis. So Q and R are strictly PSD. The system is controllable, etc. etc.
So let me poke further. Is this the minimax lower bound for a fixed T, or asymptotically it's also square root T?
Nope. It's So I'm just going to talk about the Shimkovitz and Foster lower bound, which is the one I know the best. Yeah. And it's actually a very interesting result that they provide. It's local. It's on the local minimax expected regrets. So basically, they show that for any T, for sufficiently large, but it's not an asymptotic result. For any T, for any parameter theta star, there always exists a small neighborhood where the regret associated with a parameter in this neighborhood, the expected regret, is greater than square root of T. I think I lost you.
No, I'm just thinking.
Okay.
I know how this local lower bounds are done, and I'm trying to figure out whether what you said matches what I expected to hear. It's okay. Think about it.
Okay.
Because like usually these are expressed in terms of like either on this parameter or in the neighborhood and some other parameter, the regret is going to be large. Okay, so then you say that like all together in a small neighborhood, it's going to be large. But like the size of the neighborhood obviously going to matter, right? And then there is some arbitrariness here in choosing the size of the neighborhood. You could say that like, oh, like it's kind of reasonable how you choose it, but it's still a bit arbitrary. Because like if you make the neighborhood large, obviously the regret's going to go up. And so...
Chava, may I interrupt?
Yeah, sure.
I'm not sure that this result is correct.
All right. Okay, then that's a different discussion. Okay, fine. Good.
No, not sure actually, the point that you raised, that some kind of certainty equivalence assumption is going on in the proof, that's true.
Yeah. Okay. So the version of that is that I've seen had that, and I just don't know whether it's been updated. And I was in touch with Max about that. Yeah. So okay, we all should read this paper, but
yeah, this is a very controversial discussion. Let's save the rest of it for the end.
Maybe I don't know whether any of these folks are here, but okay.
Okay, that would be cool. But okay, so assuming that this result is correct, basically it tells us that we have at least tells us that we have an exploration exploitation issue, and that we need to carefully design the exploration exploitation strategy. And so to overcome this lack of identifiability, the most natural idea is to inject noise into the system to discriminate within the self-coherent set the true parameter. So that's as I said, that's the idea behind the epsilon greedy algorithm, where the Gaussian noise is added on the top of the greedy controller. And if we look at this in the previous example, we have that injecting such noise can help in forcing the identification within this self-coherent set and allows to control to control on the trajectory the estimate accuracy and in the end the suboptimality associated with greedy controller. So the remaining question is how should we tune the variance of the noise? So how should we tune the isotropic exploration? And this we can do so by leveraging the properties of the variance of the noise. So noticing that the suboptimality function delta G is locally quadratic, it suggests to impose a square root of TDK for the noise to get the optimal trade-off. Then we have to explore all directions that are not naturally explored by greedy, which is this self-coherent set. So it's a manifold of dimension n times d. And we do so by injecting a noise of dimension d. Say to explore it properly, we have to boost the variance by a factor square root of n to explore all the directions. And basically, that's all we can do with this isotropic exploration, because the noise that we inject is not structured, and so we can't adapt further to the local shape of delta G. And it means that since we can't adapt to the differences in all the direction, we should set this the tuning of the variance in a very conservative way, at least with respect to problem-dependent quantities. That's the main limitation of the epsilon greedy strategy. But well, it has been shown to offer very nice performance, first by Mania and then later refined by the same paper of Max and Dylan, who showed that this strategy has the minimax square root of T rate, provided that the result is correct, and also offers an optimal scaling with respect to the dimension of the problem. Yet, of course, by design, can't fully adapt to the structure of the problem and usually offer worse performances than confidence-based strategy. So that brings us to the last type of exploration strategy, which on paper should overcome such limitation, which are confidence-based strategies, so building on the optimism in face of uncertainty or Thompson sampling. And they consist in following the greedy policy associated with a parameter theta t that differs from the least square estimates, but is carefully chosen within this confidence set curly C. And essentially, by choosing a parameter within the confidence ellipsoid, one can bias the estimation without damaging the closed-loop identification. And then the underlying idea behind the optimism in face of uncertainty in LQR, and in some sense Thompson sampling, if we see it as a randomized instance of it, is to leverage the following property. Among all the points in the self-coherent set, the true parameter theta star is actually the optimistic parameter. And so it's the one that offers the best performance in all those parameterization. And so it suggests that we should bias the estimation towards optimism to promote a good exploration onto this self-coherent set. And by doing so, confidence-based strategy offers a way to connect how parameter uncertainty should be reduced in light of the shape of delta G, delta J, and I agree, in a very subtle way. But it makes the structure of the exploration adaptive to the problem at hand. So it seems very good, and those strategies were actually the first to be investigated, and they have been proven to be otherwise optimal. But yet, unfortunately, they suffer from a serious limitation. So for Thompson sampling is mainly on the analysis side, because the work of Young et al. Only provides like Bayesian guarantees, or for frequency guarantees, prior work with Alessandro only holds for one-dimensional system, so quite limited. And for the optimism in face of uncertainty, there is like the seminal work of Yassin, Abaziak, and Chaba that was later refined by Faradombe, for instance, and for which we have a good regret guarantee. But it's associated with an intractable algorithm that we cannot implement, or that cannot probably find the optimistic parameter. So that's to summarize what we have on one hand algorithms based on isotropic exploration, such as epsilon greedy or explored in comets, and they have been shown very recently to be very efficient in terms of rates and in terms of scaling with respect to the dimensionality. But it's not really the end of the story, because by design, they can't really adapt to the structure of the problem and usually offers worse performances than confidence-based strategy. But for confidence-based strategy that were actually studied in the first place, we have either very limited guarantees or lack of tractability. And so if we look at this global picture, we can see that having access to tractable, confidence-based algorithm is the important missing piece here to kind of close the story. And this is what we aim to do in this work. And we aim at closing this gap. And we propose a LagLQ, an optimistic exploration algorithm. And not only we show that it enjoys a similar regret guarantee as the original optimism in face of uncertainty algorithm, it's now tractable and even computationally efficient, since the complexity is logarithmic. Okay, so let's enter into the detail and see how we get to this result.
Sorry, can I interrupt briefly?
Yes.
I forgot what it was about epsilon greedy that was not nice. So you mentioned it's square 2 regret. So
Sorry?
what's the actual problem? You mentioned that epsilon greedy has square T regret anyway. So what was the big deal with it?
The big deal with epsilon greedy is not really in terms of rate nor in terms of dimensionality. It has proven to have a nice performance. It's more on this ability of adapting to the structure of the problem. It's basically you perform an isotropic exploration, so all the directions are going to be equally explored, whereas you know that let's say they don't matter at the same.
I understand. So in the regret bounds, you don't mention anything about the dimensionality. Does it?
No,
does it scale very differently for those methods?
In the global picture that I've displayed, yes, but I've kind of hidden everything in the big O tilde. First, because I think it's maybe too much for this presentation. It starts making things quite heavy, and also because by doing so, I'm comparing results of this year with results like sometimes for a decade ago, and like the techniques in the analysis has evolved. And so it makes the comparison of the two a bit delicate. Yet, for now, the isotropic methods offers a better scaling with respect to the dimensionality and a worse scaling with respect to other problem-dependent quantities, which kind of represents this shape of the suboptimality function.
Okay, thanks.
Okay, so let's see how we get to the LagLQ results and looking at optimism in face of uncertainty for LQ. So building on this principle, it yields the following, what I call refined algorithm, which is an algorithm that operates in two phases. So at the beginning of the procedure, we input some sort of random control to perform first a rough estimation of the unknown parameter. And this is an initial exploration phase that is of constant length, which is here to ensure that the state will remain bounded over the learning process. So this is what I hinted at the very beginning of the presentation. Ensuring state stability is crucial in the LQR setting, because otherwise the state can grow exponentially fast, leading to dramatic degradation of the performance. Once this initialization phase is over, the algorithm operates through episode, following like the adaptive scheme of the original OFU-LQ algorithm, and at each policy update, an optimistic policy is computed and followed for the rest of the episode. So in the paper, and I think it may kind of answer to the previous question, we first provided some refined guaranteed for this algorithm. So we call this algorithm OFU-LQ++, but the contribution is not at all at the algorithmic level, because it's simply merging the now commonly used initial exploration with the previous OFU-LQ algorithm. But the contribution is on the analysis. And building on Lyapunov stability theory, we can carefully tune the length of the initial phase and guarantee optimal scaling for the regret with respect to T, and really close to optimal scaling with respect to problem-dependent quantities. And so, in some sense, it indicates that optimism in face of uncertainty may be the right way to go. However, we have like this tractability limitation because we need to compute an optimal policy. So policies that are optimal in the most favorable plausible environments. And this translates into this two-step minimization procedure where we have to solve a planning problem. That's the inner minimization. So this can be done efficiently through Riccati equation. But the outer minimization cannot, because it consists in minimizing a non-convex, non-Lipschitz, not even defined everywhere function over the constraint set given by the ellipsoid, the confidence ellipsoid. And so as a result, this optimism in face of uncertainty principle leads to an intractable algorithm in the LQ framework. So what we propose here is to take a different path to compute this optimistic policy. So the key steps to obtain LagLQ can be summarized as follows. So we start with the intractable original optimization problem, where we have to optimize jointly over parameters and policies. And building on the idea behind extended value iteration that is designed for the tabular case, so the MTP setting, the idea is to see parameters theta as some sort of meta control variable. And informally, what we do is that we cast these parameters into the controls and consider augmented policies, pi tilde, that summarize both the parameter and the control choice. So as a result, this allows us to reformulate the original problem up to some relaxation into a constrained extended control problem, where now we have a constraint on an augmented policy that is inherited from the confidence set. So this is basically just a reformulation, but on the positive side, we now have to optimize over policies only. So we end up with a control problem. But on the negative side, we have to handle the constraint. Say to remove the complexity of the constraint, the basic idea is to follow the standard path of Lagrangian reformulation. So we express the constraint in a functional way using a function capital G, and we use a Lagrangian formulation to replace the constraint by the maximization over a Lagrangian parameter mu. And at this step, we replace the complicated optimization problem over parameters and policy by a potentially equally complicated optimization problem over augmented policies and 1D variable mu. And this path might be interesting if and only if we can leverage duality to permute the order of the max and the mean and end up with a much simpler optimization problem. But to do so, we have to be extra careful when following this plan, because we need to end up with a control problem that we can actually solve. And remember that LQRs are kind of a singularity among the continuous state and action control problem. So this is why there are two warnings in this plan, because we have to be careful and actually perform a constraint relaxation to ensure that the LQR structure is somehow preserved along this path. So that's the plan and the global picture on how to obtain LagLQ. So let me know details separately to skip step. So let's first construct the extended control problem. So we have to control the state dynamic in two ways. We have to find the optimal sequence of control. That's the planning problem. It's highlighted in red. And then we have to choose the optimistic matrices A and B, summarized in the parameter theta. And this is the optimistic search. It's highlighted in blue. And as we previously saw, the challenge lies in the optimistic search, which has to be conducted on the confidence set curly C to promote a good trade-off between exploration and exploitation. So in order to isolate the optimistic search, what we do is that we first reparameterize theta in curly C around the current least square estimate theta hat. And theta hat is the center of the ellipsoid. And as a result, we replace the choice of a parameter theta by the choice of a deviation delta theta from theta hat. And we can plug this back into the linear dynamics and basically cast the choice of a deviation delta theta into a choice of an optimistic perturbation, WT, that varies from line to line. And this is how we put back the parameter into the control. Because what we obtain is an extended linear dynamic with two different kinds of inputs. So we have the original control U and the perturbation W, which is here to favor optimism. And this allows us to turn the optimistic search into a control problem where we seek for an augmented policy pi tilde that addresses both the choice of the control, so that's the red component by U, and the choice of the perturbation, it's the blue component by W. Okay, but by doing so, we inherit a structural constraint from the confidence set that we encode through a function small g on the triple state control and perturbation. and this is where the first warning arises, because we have to be sure that this constraint is somehow compatible with the LQR structure. And recall that it's a singularity, so we really need to preserve this LQR structure. So when we dig a bit more into this constraint, we see that it has to hold for all the triple state control and perturbation that we traverse on the trajectory. And on the bright side, the function small g is quadratic. So this is compatible with the linear quadratic structure of the objective. But on the negative side, it must hold uniformly in some sense. And this is in sharp contrast with the long-term average nature of the objective. And to cope with this difficulty, we begin by relaxing the constraint, and we move from a uniform constraint over the state process to a long-term average criterion. And this is now encoded through the function capital G, and this will be the constraint that we will consider. So of course, it's a relaxation, because obviously the former implies the latter. And this relaxation had the advantages of being, well, quadratic, because this is inherited from the original constraint. But now it must hold on average, and that's compatible with the LQR nature of the objective. Okay, so thanks to this reformulation and relaxation, we obtain like this novel optimization procedure to compute the optimistic policy that leads to a slightly different algorithm. So at a very, in a very abstracted way, at each policy update, what we should do is to solve the extended control problem to get an augmented policy pi tilde, and then extract from it the component pi u that corresponds to the control, and follow pi u for the rest of the episode. And of course, a potential drawback of this approach is that we had to perform a relaxation to get there, and this may be harmful, but this following result ensures that it's not. By doing so, we guarantee that the policies that we compute are indeed optimistic, so this validates the effectiveness of the approach. And second, the relaxation does not compromise the regrets, and it still addresses properly the exploration-exploitation trade-off. So we have similar rates and similar bounds than for the original OFU-LQ++ algorithm. So that's a promising intermediate result, and we are now left with solving this extended LQR control problem. Say, we have a constraint, and this poses a problem, and so to remove the constraint, we use Lagrangian reformulation. So we introduce this parameter mu, Lagrangian parameter, over which we have to maximize. And notice that those two problems, they are always equivalent. So the interest of the Lagrangian formulation resides in whether we can commute the max and the min, otherwise it's not going to make the problem easier. But unfortunately here we are relatively far away from the standard optimization framework, because the function j and g involved in the Lagrangian problem are way more complicated than nice complex functions. So despite this complexity of the objective and constraint, what we show in this work is that strong duality does hold, which is the second important result. And as a consequence, we can equivalently permute the min and the max to find the augmented policy, and that will make our life easier. So this statement was actually the most challenging to get. It took us like something like a year and a half to properly derive it. And actually its impact goes beyond adaptive LQR, because it holds for any LQR under quadratic average constraint. So it's more a result on the control theory side than really on reinforcement learning. So let me pause for a sec and discuss it in more detail. So if we look at the left-hand side of the equation, it really corresponds in a one-to-one mapping to the constraint, the original constraint control problem. So the challenge lies in showing that the right-hand side can attain this value. Because by weak duality, we have that the inequality from left to right is always satisfied. So the optimal value for the extended constraint control problem is always greater than the dual function. And so formally, if I denote a J star, the optimal value of the constraint problem, it's greater than the maximum of the dual function, curly D, which is given as the minimum over augmented policies of the Lagrangian objective. So the question here is whether the dual function attains its maximum and whether the maximum coincides with J star. So by construction, we already have the following nice properties. The dual function is concave. This is always true. It's like standard duality results. But more importantly, the Lagrangian resembles an LQR problem. And so one can hope to obtain curly D as the solution of the Riccati equation. So that's where the warning gets back, because if you remember what we saw a couple of slides ago, it's exactly why we performed the relaxation of the constraints in the first place. So that's the good news.
I think, Mohammed, you have to mute yourself.
Yes?
Mohammed, mute yourself.
Okay, I thought he wanted to ask a question. Okay, so the good news is that the Lagrangian resembles an LQR problem, and it means that we should be able to obtain curly D as the solution of a Riccati equation. So we have this warning popping up because it's not really as easy, and it only resembled a standard LQR problem. So if we go into more details, what we see is that for a given value of mu, this dual function is given as the minimum over policies pi tilde of long-term average quadratic cost under linear extended dynamic. But the cost is now defined thanks to a symmetric matrix C mu that depends on the Lagrangian parameter. And it can be decomposed in two parts. So the first part, C, corresponds with the original LQR objective, and thus is PSD. So we are definitely in the standard regime of the linear-quadratic regulator. But the second part is CG. It comes from the constraint, and it has both a positive and a negative part. And this might break the positiveness of the cost matrix as mu spans the real line, the positive real line, and hence put us away from the standard LQR framework. So this is what I highlight in the figure below. As mu increases, the cost matrix that we have become less and less positive, and at some point, that's I denote mu plus, it stopped being PSD. Then on the right-hand side of the figure, when mu is very, very large, so larger than some value mu minus, its important first block becomes negative. And what's happening in between? Well, the inertia of C mu varies when mu increases, and we have both positive and negative eigenvalues. So what's the impact of this into the dual function? Well, in the two extreme regime, it's relatively easy. So when C mu is PSD, we're in the standard LQR framework, and we can obtain d mu as a standard Riccati solution. When mu is very large, larger than mu minus, we can show that there exists no stabilizing solution, and the problem is degenerated. And the interest resides in what's happening in the middle. And it turns out that we can go beyond the standard Riccati framework and guarantee that it exists a point, a breaking point, mu tilde, somewhere in between mu plus and mu minus, such that below mu tilde, a Riccati solution still exists and coincides with the dual function. And so this immediately translates into properties for the domain of the dual function. So before mu tilde, we're inside the domain, things are well defined and can be obtained by a Riccati equation. After mu tilde, we're out of the domain and the problem is degenerated. So in light of strong duality, what we need to show is that d mu attains and reaches the optimal value J star within its domain. So this is what I illustrate here. So J star, the dotted line represents the value of J star that curly D must attain. And what we obtain is the following. So let's say in the standard Riccati regime, we have that d mu increases but do not reach the value J star. And it means that if strong duality holds, it has to take place in this generalized Riccati domain. And so the good news is that we know that things are well defined here, but the bad news is that we get away from the standard Riccati framework, and technically speaking, although there exists results in the literature for this regime, it requires to shift the analysis from the time domain to the frequency domain, or said differently, we have to move from the real space to the complex space, and this makes things heavily more complicated. But we can show that the dual function, in the worst case, behaves like that. It keeps increasing, and eventually it converges to J star when mu approaches mu tilde. But it only converges, so it never really attains the maximum. And it implies that strong duality holds only in a weak sense, where by weak I mean that we don't really have min max equal max min, but only min sup equal to sup min. But that's a start. But it's not enough to derive an algorithm from it, because we are not interested in minimizing the duality gap here. We are interested in finding a policy that satisfies the constraints. So we really want to get to a maximum. So at the very high level, we would prefer to be in this setting, where the maximum is strictly attained within the domain, and then for algorithmic stability reason, away from the border of the domain by a sufficient margin, because things get very weird in there. So in terms of duality, it corresponds to the case where we have strong duality in a strong sense, so where we have min-max equal max-min. So let's be honest. In the simulation I conducted, I never encountered the bad case where strong duality holds in a weak sense. Yet it's still possible that there exists problem where it's the case. And well, we suspect that it coincides with a class of system of zero-level measure, which is why we cannot really get to it. But nonetheless, we have a way to overcome this difficulty. And essentially, if we're in this very nice configuration where we have an isolated maximum, maximizing such function is very easy. It's a 1D function, so simple dichotomy search will do the job. And so what we do is that we conduct a maximization in 2 consecutive passes. So we do a first pass, and we try to, and we detect whether, we are in the bad configuration or not. And if we end up by some margin dealing with this weak strong duality, we apply a perturbation to the problem, and we rerun the maximization. And the perturbation we apply ensures that that we end up in the nice case where strong duality holds in a min-max sense. So, yes?
Yeah, so you have a lower bound on mu tilde, or like, do you know the value of mu tilde from somewhere?
So you don't really know. So you have the lower bound because the lower bound is mu plus. You have the upper bound because it's mu minus, and those are quantities that you know. And for instance, it helps you when you want to run.
Yeah, but like mu plus wouldn't be a useful. Yeah, you need something.
No, it's I mean, it can really be everywhere between mu plus and mu minus, and depends on the structure on the problem.
But you have mu minus and mu plus are not problem-dependent constants, so you can pre-compute them and then search that space. So,
yeah, mu plus and mu minus are not problem-dependent constants in the sense that they depend in the least square ellipsoid. The confidence ellipsoid that you use to construct the constraint. So you know them prior to the maximization. So you really can compute everything. And if you really want, you also can compute mu tilde. So it has a well-defined, it's a well-defined quantity. But as I said, you know, its definition is given in the frequency domain, and it's kind of it's a bit complicated. So
and mu plus and mu minus can be computed efficiently, I suppose.
Oh, yeah. It's like the minimum eigenvalue of the design matrix and the maximum eigenvalue, something like that. So it's, I mean, really straightforward.
Okay.
Okay, so anyway, even if we are in this bad configuration, okay, we can apply a perturbation to the system. We detect it, we apply a perturbation to the system, and we end up in the good configuration. So this is why we do 2 passes. And then we do a simple maximization by dichotomy. So,
sorry,
for those who are, yes?
Will the size of this perturbation matter? Do you have to carefully choose that? Or?
Yes. Of course, you want basically the perturbation is by 1 over square root of t, so that it doesn't impact the regret, because you just find an approximated solution.
I'm also worried about like problem-dependent constants, whether the perturbation can be chosen in
the perturbation can be arbitrarily small.
It's just that it's where it becomes really fishy, right? This argument, if you make it
not really. So basically, basically what
really bad state, then how can it help if the perturbation is really, really small and there is some stability going on?
So I can illustrate that. So basically, if you are in this bad configuration, if you apply whatever perturbation small enough, you will end up in the good configuration. The question is how far the maximum is from the border of the domain, and this is kind of harmful for the dichotomy because it plays a role in the curvature and the smoothness of the dual function. But like, let's say the less smoothness you have, the more difficult will be the dichotomy. But since the dichotomy It's very fast in this 1D setting. You know, it's logarithmic complexity. You can afford to input any small perturbation that you want. I mean, as small. I can even put like a 1 over t to the 4 or something like that. And it's not going to be that harmful for the for the maximization. But definitely there are a lot of subtleties. So the nice thing is that we can characterize everything and check that things compensate in a nice way. So this perturbation,
like either this never happens, or if it happens, then like there is some subtlety here.
on paper it can happen, but I never encountered that in experiments, because I guess it's zero Lebesgue measure sets. I think we can prove that. But I was not able either to find a counterexample where really we have these kind of issues.
All right.
But well, again, so this part of the analysis takes place in the frequency domain, and so it makes it really complicated to get some intuition in the type of system that we should construct to have this problem. But we can really deal with. We really have a procedure that fully addresses this complexity, this issue without being impacting the complexity cost. So, not entering into the detail, but you can have a look at the paper. We have this full characterization of the dual function. What is this behavior close to the border of the domain, and its smoothness and all those properties, and it ends up with the algorithm that characterizes and addresses all those cases. But okay, and so if we forget about all those subtleties, what we only have to remember here is that strong duality holds up to some perturbation, and that to solve the constraint problem, we just have to maximize the dual function. And the domain of the dual function coincides with where we can compute it solving a Riccati equation, so it's very efficient. And further, it's a nicely strictly concave function, so we can, efficiently solve it by dichotomy. So overall, we are very happy, and we have an algorithm that we can solve at a logarithmic complexity cost. And the logarithmic complexity cost directly comes from the dichotomy.
Actually, just one last question about this D and the bad case. So, like, how does this algorithm work? Like, you can point away D mu?
How does the algorithm work to detect that we're in the bad configuration? Yeah. So basically, it's a matter of smoothness. So you go through you kind of span.
What is that you can compute? Like, I'm a little bit lost.
So here you can compute basically everything. So for each mu, you can compute d mu, you can compute its gradients, you can compute its Hessian.
Okay.
So you basically have all the quantity that you need to check whether you have sufficient smoothness and so on and so forth.
And you approximately do that or something like that. And then if
well, you do that by solving Riccati equations. It's all about Riccati or
what I'm saying, the approximation is like to detect whether the curve always goes up, or like there is an infinitely small drop at the end. Like you will never detect that, of course, but you don't need it, right? Like.
Yeah, the thing is that, as I said, we need to have the nice case, to be in the nice case by some margin. So as soon as we detect that, let's say the level of smoothness is below the desired threshold,
okay,
we directly apply the perturbation and we switch to the second pass.
All right.
Okay. So yeah. In the end, we are relatively happy. We can solve this dual optimality problem at a logarithmic complexity. And so, to summarize, we obtain this algorithm LagLQ, where at each policy update we find the augmented policy pi tilde solving the dual problem, and then we extract and follow the optimistic policy pi u from pi tilde. And overall, we have an algorithm that enjoys the regret guarantee that we saw before, so square root of t with decent problem-dependent constants at a logarithmic complexity cost. So that's basically the end of the talk. So here are some take-home messages. We focused here on confidence-based exploration for LQR, and we showed that the idea behind extended value iteration can be transposed from the tabular setting to LQR. And this allowed us to derive the first efficient optimistic algorithm for adaptive control in LQ. And somehow this result guarantees the existence of confidence-based algorithm, namely LagLQ, that are competitive with isotropic algorithm based on epsilon greedy, not only in terms of regrets, but in terms also of computational cost. So now the remaining interesting question is whether one may be superior to the other in practice. It's unclear, even though theory kind of suggests that confidence-based is better. It's, you know, algorithms are not always designed in a tight way. So what we did is like we conducted some preliminary experiments really quickly and compared LagLQ to CECCE, the epsilon greedy algorithm of Szymkowicz and Foster on very synthetic example. And what we show is that what we see here is that, okay, both have some kind of story of T regrets. So it's expected from theory, but they have a different constant that is problem dependent. And this kind of suggests that optimistic exploration may be superior in practice. So of course, those preliminary experiment has to be taken in caution, with caution. And very likely the gap in performance may also come from looseness in the analysis, in the design of your algorithm, you know, a confidence set that is not as tight as possible, etc., etc. So we have to be careful, but I believe that the comparison between the two approaches is now a very interesting and challenging question that remains open, but that we can address now that we have an efficient confidence-based algorithm that we can implement in practice. Okay, that's it for the talk. Thanks a lot for listening. And if you have extra question, try to provide an answer.
Yay!
Yay! Thank you.
Thanks.
Thanks.
Marc, I have actually two questions.
Yes.
One refers to something on slide 5.
Yes.
About solving the Riccati equation.
Yes.
This complexity of cubed with respect to
Yep.
dimension is. Do you know, like, for which algorithm this complexity holds?
Okay. Yeah. So I don't have any way to display the Riccati equations, not in the slides. So basically, when I'm talking about cube, I'm thinking of what is called the Van der Waals method. Okay. So basically, the Riccati equation is like a fixed point, and it's again, if we move from the time domain to the frequency domain, one can translate this like the fixed point of this Riccati operator into finding an invariant subspace for an extended matrix pencil. So it's kind of a generalized eigenvalue problem. And so to solve, so Riccati coincides with a generalized eigenvalue problem in the Z space, in the complex space. So it's based on QR and QZ decomposition.
And it is not an it's not it's not an approximation algorithm. It gives you the exact solution, you mean?
Well, at machine precision. I mean, it's really similar in nature to compute as computing an eigenvalue. So if we're okay to admit that when we compute an eigenvalue, we obtain the true solution, at least up to machine precision, then the Riccati equation gives you the optimal solution, the exact solution.
I guess maybe the question is whether if you take the real arithmetic, so you can do algebraic computation exactly, and there is n cube number of operations that you need to take, and that you get the exact solution, right? So if you run Gaussian elimination, for example, to solve a linear equation, there is no errors there. So is this the same type of computation, or is it like a numerical computation where you probably exponent equation approximate and there is some epsilon lurking them, and the epsilon can be put really small, but the dependence on epsilon is so small that you don't know. I think that was the question.
Yeah, so I'm not sure I fully heard everything, but yes, I would say that, I mean, since it's like an eigenvalue problem, generalized eigenvalue problem, it's based on QR decomposition, so it's similar to like inverting a linear system. So I would say that yes, we have the exact solution. So that's the real power of Riccati equation actually, and one of the most interests in this linear quadratic regulator in terms of planning.
And in slide 8, about divergence of the greedy algorithm to that manifold.
Yes.
Like which result is stating that greedy will not converge to the truth or something like that? I mean, is it proven that does not converge?
Yes. So it's proven. So it's difficult to give you a proper pointer. So first, it's always converging in distribution. So this comes from the structure of the least square. Okay. Then all we need to check is that this distribution is not degenerated. And this, I think, so to this we just have to check the eigenvalues of the design matrix, and for greedy we can prove, I think that I'm pretty sure that it has been proven for greedy. So honestly, I can't point at any results. I think it's not that hard to derive it. Maybe Chaba has a pointer.
I don't have the pointer. Maybe others have the pointer.
I don't think that it's proven.
Okay, but the proof would be on some diffusion arguments, I guess. Right?
Yes. Yeah. What you want to show is that the support of the limiting distribution is not degenerated.
Well, it's a little bit stronger or weaker here, but yeah, I don't think this result is proven.
Well, if it's not, it might be funny to look at it. I'm not sure that it's not proven, essentially because, I mean, when you start digging into the literature about all this stuff in the 80s, I mean, it's huge. It's not necessarily, the literature we are used to look at in the reinforcement learning, but there is a lot of stuff on identification, self-tuning properties and stuff like that, and a lot of results has been derived.
Yeah, but this one is not being proven, and the intuition is that this small randomness which comes from the noise in the dynamics, it is enough to give you some kind of very weak convergence, so that those degeneracy that you were referring to will not happen in long enough time, something like that. In the intuition is that.
Well, that would be very surprising.
Yeah, so just like additional exploration that you add, the internal noise itself gives you a little exploration, something like that, intuitively.
But intuitively, like, you cannot really escape from this identification limit, right? So if you were on the manifold, all these thetas are going to look the same to you because of the closed loop dynamics, and somehow the perturbations are not sufficient to escape this.
Yes.
That's my point. I think it can. It does not give you the square root regret, but it gets you out of this closed loop identification equation in SC. It gets you out of that.
So I don't think so, and I think so. Well, then I mean, I have no pointer for any proof, so it's difficult to. I don't think so for two reasons. First, in terms of let's say level of exploration that is induced in this system. So when you're greedy, basically you try, at least in the 1D example, you try to estimate two matrices A and B with a single noise, so a single input. So then you have like 1 degree of freedom too much. And second, it's known that linear quadratic regulators are not self-tuning, in the sense that the greedy strategy will fail to achieve consistency, even with a small amount, by a small amount. So maybe the results for this property can be found in those papers. I'm thinking of, for instance, the early paper of Kumar or Campi about that.
It doesn't. Even in Polderman setting, he does not discuss this one.
Okay, so you just discussed the structure of the system. No. I mean, it's a very interesting question. I mean, if this were the case, I mean, it would be a super cool result.
It seems we identified an interesting problem to poke around.
But if I can just add a comment on what you just say, Mohammed, this is what is. This might happen when we move to the LQG, so when we add partial observability, what you say, because partial observability does induces in some like implicit way extra noise, because you control like not the real state but the belief state that is a random realization of the state, so it naturally induces a bit of extra noise. So for LQG, I would buy this result. For LQR, unclear. needs to be investigated.
So Mark, I had a question regarding your loop in optimizing mu. So there, you just go into all this trouble to avoid these kind of like weird case where your mu tilde is causing some trouble. But then in the end, you're saying that you're going to solve this outer maximization problem to some epsilon precision. I thought that you went into this trouble to make sure that your solution is feasible, which really does require you to find the exact max. But then in the end, you're saying that you're still happy in an epsilon optimal solution.
I mean,
like, how is this? Can you explain?
So we solve it by dichotomy. So we really have, you know, this kind of epsilon precision. What we can afford is to be only like epsilon optimistic. So we don't necessarily need to be optimistic, but if we're optimistic by, you know, 1 over square root of T margin, it's not going to affect the regress. What we would, the desirable property, however, is to obtain a policy that is strictly feasible, so strictly within the confidence sets. Otherwise, it may be a bit more touchy to handle it. But in any case, we have a bit of margin. So it's not a problem to find a policy that is, you know, an epsilon approximation, but it really has to be a policy that is feasible, or at least only epsilon away from the constraint. And this is why we have troubles in the first place. It's because, you know, if we're in this configuration, even though we get really, really close to J star in terms of, you know, in terms of duality gap, you know, the policy associated with these points might coincide with a policy that has, you know, that really violates in a bad way the constraint. So this is also why we can't really, you know, operate in this bad, like weak, strong duality case.
I see. So there's like a lot more trouble happening in that regime, and once you're out of there, you can be happy with suboptimal or like slightly suboptimal solutions. Because you can still extract a legitimate policy from that, and you know that is going to be like reasonable in terms of this epsilon, the accuracy that you're getting in this loop.
Yeah, well, this regime is actually very interesting. I mean, I mean, we provide some characterization in the paper, but when mu gets close to mu tilde in this case, you know, things gets bad in the sense that, you know, the function becomes non-Lipschitz. The solution of the Riccati equation that corresponds to d mu is almost ill-defined. So we really have a bunch of policies or linear policies that offers the same costs. So really a lot of things, a lot of bad things happen there.
Right, I see. And now looking at the chat, it appears that there was some confusion by what you mean by dichotomy search. Is it just a line search or bisection?
Oh, it's a bisection method. So you start from mu plus and mu minus. It's the two extreme of the interval, divided by 2. Check whether you meet the constraint or not. If not, you know, choose your side, divided by 2 extra. So it's really like a bisection.
All right, and you don't need any crazy assumptions about the functions to do this.
No. Those results actually holds in general, and as I said, it's kind of a control result in the sense that it's somehow unrelated with learning in LQR. It's all about, you know, LQR under average constraint.
All right, gotcha. Very nice.
Just a follow-up. So this is adaptive, right?
This is adaptive in
efficient dichotomy with respect to the increase of perturbations.
Not sure to understand. Can you repeat the question?
I just had a follow-up with respect to the efficient dichotomy search, which is which should be adaptive in the case of the epsilons that the mu that we are trying to find. If I look at the paper, it says the process whenever goes to mu t minus mu L, there is a difference between how do I say it, a certain section in which it's adaptive. I'm a bit yeah. Mhm.
Are you saying that the stopping criterion for the bisection changes?
Yeah. With respect to
Yeah,
the
sure. To the curvature of the problem. Yeah, it's a bit more simple than that, because since, as I said, during the first pass and also during the second pass, we are unsure about the level of smoothness of D and how Lipschitz it is, and which kind of configuration for the strong duality we're facing. And so basically we have to adapt and adjust dynamically the stopping criterion so that we have, the accuracy in terms of mu that is sufficient with respect to the level of smoothness of the dual function that we don't know a priori.
Okay, cool. And we use Lyapunov's equation here to go to.
Yeah, all the quantities involved in this dichotomy search. So the dual function. So the dual function is computed by Riccati. Its gradient is computed by Lyapunov. Thanks to the solution of the Riccati, the Hessian is computed by Lyapunov. Anyway, all of these objects here can be obtained by Lyapunov equation, and you can think of the Riccati equation to be the minimum of some Lyapunov equation. So, for a fixed controller, the value of the cost is given by a Lyapunov equation, and the minimum costs, so in the optimal controller, is given by a Riccati equation. So those are the equations that we manipulate over and over during this work.
Okay, thanks.
You're welcome.
All right, so I think Nan had some questions regarding epsilon greedy and like the efficiency of that versus optimism. Nan, are you here, and can you ask your question? Maybe he's gone now. So like Nan was just asking if you can like really see the suboptimality of epsilon greedy just by looking at the bounds and the properties, or do you just sort of like disagree with the philosophy of epsilon greedy? Like, is it easy to quantify these differences? Chaba, you're muted.
Yeah, this was for the off-the-record conversation starting, right?
Well, I can still answer right now. So it's an interesting question actually. So two level of answer. So the first, I mean, just to put it back in perspective. When we started this work like 2 years ago, no epsilon greedy result at all were available. At least, I mean, the result that we have for epsilon greedy was like t to the 2/3. So the challenges was not at all to try to beat epsilon greedy, but just trying to have a method for which we have theoretical guarantees and that is efficient. So, but then, while working, those results for epsilon greedy pops out, and it's true that it triggers an interesting discussion. Then, from a philosophical point of view, yes, I do believe that like confidence-based strategy are more adaptive and so are on paper better than epsilon greedy. Sadly, it does not translate immediately in terms of bounds, but I can show you the difference. But just the high-level reasoning is the following. The nice thing of epsilon greedy, and especially in LQ here, is that you're going to operate through episodes of fixed and deterministic length. And you apply a random noise in those episodes. And so it makes the analysis way more easier because you have some kind of IIDness that arises and you don't really have this adaptive structure. For instance, it means that you can really do all the bounds episode per episode and then sum them all. Whereas when you do, let's say, adaptive techniques, you don't know when you're going to update, it's a stopping time, and you have to control all the sort of things, ending up with, I think, quite loose analysis in, for instance, the bound of the state. This is the crucial part when looking at all the results, or the concentration inequality, etc., etc.
And can you get high probability bands if you do epsilon greedy, because it feels that you're randomizing like very few times, and
no.
You run the risk of doing something really stupid for a really long time and then
No. They have a high probability bound. I mean, really, the scaling is optimal in a lot of aspects. So let me, if you want, I can show you the comparison of the three. Because I think it's
nice.
interesting. So if you go to the paper, it's there. So this regret is the one of epsilon greedy of Foster, where I try to highlight all the, let's say, the problem-dependent quantities. So we have the square root of T regime. We have that D, the dimension, it scales linearly with D, the dimension of the control, square root of N, the dimension of the states. And it has this like quite byte dependency on P star. P star is the optimal solution of the Riccati equation for the true parameters. So this is really this kind of problem-dependent quantity that we try to avoid. And this can be huge. Okay, and when you try to do like more adaptive algorithm, you get this. So for instance, the result for OFU so we also have square root of T. We also have square root of N. We're slightly worse in terms of D. So we don't have D, we have N plus D. So sometimes it's the same, sometimes N is way larger than D. This definitely comes from a looseness in the analysis. It comes from the confidence bound. But there are no N plus D directions that are badly unexplored, only D. And so this should pop up here. I think it could be refined by the analysis, but it's not easy. I mean, we need to get back to the confidence bound of Yassin and Chaba, and on this point, the epsilon greedy allows like the analysis of Max and Dylan to be way sharper with respect to this kind of quantity, so they gain here. Then we have this problem quantity here, P star, and we see that it starts to be quite better. Notice that like in the 1D experiments, P star is usually of the order of like 10 or something like that. So it makes it a big constant. And then what
is it the looseness of the analysis of the epsilon greedy algorithm, or is that dependent 11 over?
Yeah, that's the question. That what I said was an open question, how to compare the two. It's difficult, If you compare it in terms of algorithm, then you know that epsilon greedy has a structure of the exploration that is hard-coded. So the looser the analysis, the worse the algorithm. And so it makes it difficult to compare it empirically. Then if you want to compare the bond, then you never know whether it really comes from looseness in the analysis or intrinsic behavior of the strategy. So it really makes the comparison difficult. Yeah, but here you see that we can sorry?
There is no conceptual difficulty, just that some work needs to be done.
Yeah, true.
You should do theoretical tuning and then do the lower bound for the algorithm. That's it.
Yeah, well, I don't know what is the dependency in the lower bound for this quantity. I should check. But for sure, we see that we can really refine this problem-dependent constant. The drawback is that when we do that, sorry.
What's your kappa?
Okay, and then the drawback of that is that kappa is the trace of P star. And so the drawback of this is that in many cases, kappa scales with N. Okay, so basically we're off by N for OFU square root of N, sorry, and we're better in independent constant. So it's very depressing. And again, this really comes from a looseness analysis, but it's very difficult to fix. At least I haven't found a way. It comes from the way we take into account the states, and since the proof is way more dynamical, let's say, for optimism in face of uncertainty, we have to follow different proof paths. And so we can't really use the same tool, and we end up with this quantity that, let's say, on principle should not appear. But it's true that it makes the comparison of the two bounds a bit depressing. And then you have, this is a looseness. I think the looseness from the regret of epsilon greedy to the regret of optimism of uncertainty really comes from looseness in the analysis. Okay. Then the second looseness is when we go from the regret of OFU so the real optimism in face of uncertainty algorithm that we would like to use, to LagLQ, then we're again off. We're a bit off with respect to problem-dependent constant, but we are off by kappa. And this is likely to be incompressible in the sense that it comes from the relaxation. So when we relax the constraints, we really relax the problem. And so we pay it a bit in the regrets. So the question, how much should we pay? Again, difficult to say. I would say that the first stage is to try to fix this regrets for of OH2++, and then let's see how it translates in the looseness for Lagrange. And this requires some kind of it's technically speaking might be picky. So, well, I mean, there's still work to do towards the in-depth comparison of the three. Let's see. I'm resting a bit for LQ for now, but it might be worth digging into it. Yeah.
All right.